So, the audience, please welcome Laurence Parker here on the stage with us.
Okay, thank you. So today's presentation is to talk about improving the transmit noise on the SATURN radio, but I'll tell you a little bit more about how that came about first of all. How do we move on to the next slide? No, just click it. Okay. So I've talked about this before at this forum. This is the SATURN radio hardware. This is now the processor board that's in the Anand G2 radios, the Apache Labs product. So you can go and get one if you want one. It's really in two halves. The left-hand side has got the analog parts a bit like an Orion Mark II with two A to D converters and a D to A converters. The right-hand side is like a Raspberry Pi 4 compute module. Well, it is a Raspberry Pi 4 compute module. It's like the I/O board. It's got all of the extra interfaces that are on the I/O board. And the SATURN radio that we've created is essentially made up from the digital processing in a Xilinx FPGA in the left-hand red box, and then software processing on the Raspberry Pi in the right-hand red box. All that's completed and working, as I reported last year, but we've had some things to fix along the way. Now, I've talked about this product as it's been developed for over quite a while. So about 2020, I came here and presented, or I would have come here, but COVID stopped, so we had to do it remotely. I presented about how I've used Xilinx FPGAs with their graphical design environment, which is part of the Vivado suite, as the way to create the FPGA for both transmit and receive. And the fact that it's a graphical design environment and all the FPGA cores, or at least most of them, are provided by Xilinx, means that that's a more accessible approach to people who are not intimately familiar with doing FPGA design. Then later I presented what are the options to connect the FPGA to a processor and described some of the different approaches that can be used. The one we've used is to use PCI Express, but there were others. And last year I described some of the finishing off of the radio to get to the point that it was ready to be used. A bit before that, about 6 years ago now, I came here and presented about how to make essentially a front panel controller with knobs and push buttons to turn an SDR from being something that you use connected to a PC to something that was a bit closer to a normal radio. And that I presented with Kjell Carlson, LA2NI, who, as we heard earlier, is sadly silent key now. So what have we been doing for the last year? Well, the radio works, but with this type of radio, there's always more things to be done. We've improved the data transfer software to avoid some little audio cutouts that were happening some of the time. Christoph has presented about changes we've made to improve the performance of CW. So you can now select essentially the ramp width on CW to improve the spectrum occupancy. We've integrated to an antenna tuner, and we fixed a protocol issue that was affecting all of the HPSDR radios that was causing some energy to leak out onto essentially onto antennas that were selected not for transmit, that might have a sensitive high gain receiver that was capable of being destroyed. All sorted, so we've been reasonably busy, but along the way we also found out that the transmit signal was not quite as clean as it should have been. So Christoph has presented about how to improve the fidelity of a CW signal, but what we found that with the basic G2, Christoph's noise floor of about minus 120 dB, I wasn't even getting as good as that. And today I'm going to describe how we fixed it. So what should a transmit signal look like? Well, if you put your radio onto tune or just key down, ideally You should get a single signal at a single frequency and absolutely nothing else. Unfortunately, that's not really practical with any electronics that's available today. And we end up with some noise sidebands. So we end up with a signal that at frequencies either side of the signal has some energy. You can't get away from that, but ideally, if you were 10 kilohertz away from your wanted signal, those should be about minus 140 dBc per hertz. That's not easy to measure. If you go to the exhibition hall about 400 yards over that way, you'll find a few stands selling spectrum analyzers for a couple of €1,000. Those will not measure that. They're not good enough. So, Christoph presented a novel measurement technique. What Christoph said is, we've got a high-fidelity receiver. We've got a coupler after the transmit amplifier that will couple off some signal to come back into another A to D converter that can then go to the processing. And that essentially gives you a way to measure the transmit signal and then make use of all of the DSP that's available in Thetis or Pi HPSDR to make a narrowband filter that means you can then see signals either side of the transmit signal. And Christoph presented some measurements that suggested he was getting down to a noise floor a few kilohertz away of minus 115 dBc. Well, mine was quite a lot worse than that, so something had to be done. So where's it coming from? Well, the first thing I thought about is it a transmitter fault? We knew that on my SATURN board, and this is something that everybody else's SATURN board did not have. If you look on the display, this is from Pi HPSDR, you get the wanted signal in the middle. That box is unfortunately not quite in the best place, but never mind. But at plus or minus 14 kilohertz, I was getting two spurious sidebands. I don't know exactly where they came from. There was some kind of assembly fault on the D2A converter, we think. But nevertheless, they were there at about minus 60 dBc, and maybe that was the cause of the problem. Well, we never could find out what was causing those, and in the end, we replaced the SATURN board. Those signals had gone away, but it didn't affect the rest of the noise performance. Consequently, from the perspective of my radio, things were better because I didn't have those spurious, but nevertheless, there was still a problem. Well, where can that have come from? Essentially, our transmit chain creates a direct sampled HF signal from a D2A converter. And then the signal and any spurious can only come from three places. It can be affected by the quality of the D2A converter, by phase noise on the D2A converter clock signal, or on the numerical behavior of the signal processing behind it. Well, Christoph was getting results 20 dB better than mine, using a design that has the same D2A converter and at least the same design intent for the clocking. There was very slight differences in the clock, but not that ought to show up to the tune of 20 dB. So the place to look was in my signal processing. So how was I going to go about investigating it? Well, I learned a long time ago, you can't just try making some changes to the FPGA and then see what happens. If you do that, at best, you'll get one new result every day, because that's how long it takes for the design to compile. And it's not scientific, it's a bit like stabbing in the dark to see if you can find something. So to try and do better than that, we need to understand exactly what the hardware, as it was implemented, achieves. And to do that, you need bit-true simulation. Well, if I was doing this professionally, I'd probably turn to MATLAB. And there's bit-true toolboxes available for MATLAB. And in return for a few €1,000, I could probably make some progress with that. But this is an amateur application, and I don't quite have those few €1,000, so I needed to do something simpler. Well, last year I described an approach to this kind of thing that does seem to work. I can get a bit true simulation of my signal processing from Vivado. So I essentially run a version of my transmit chain in the time domain simulator, and that gives me a big list of essentially all of the 16-bit numbers that go to the D2A converter. I can write those to a file and then go to a piece of software called Octave, which is kind of like a copy of MATLAB, and read in that file and display the samples in the frequency domain, and then add a little bit of extra processing to try and improve the display. And that's the approach that I've used. So it's giving me a way of doing bit-true simulation of what my transmit chain's doing, but without having to spend a lot of money. So what's the transmit chain? Well, it's very similar to the receive chain that I described last year. If you were making an analog radio, you would start by filtering the signal from your microphone, mixing it with an oscillator, and that will give you a modulated signal. Well, in the digital form, we do something similar. We filter digitally, we interpolate the signal up to the full sample rate, and then mix it with a signal from an oscillator. Well, to make that happen, a mixer is a complex multiplier, and an oscillator is a thing called a direct digital synthesizer. And that gives you essentially the complete transmit signal. By tapping off some signals from that flow graph into my simulation, I was able quickly to determine that the cause of the problem was in the direct digital synthesizer. So what's one of those? Essentially, a direct digital synthesizer is a digital local oscillator. And the way it works is by having a word that's this point marked n bits here. It's a digital word that represents the phase of the signal that you're going to transmit. That didn't work well, did it? Let's see if I can go backwards. Anyone know how to drive this in? Yeah, the instructions are in German, and unfortunately I don't speak that. It's going to get me backwards, I think.
Sorry, what do you need to?
No, I've been able to go back now.
Okay.
I was going forward one slide on each click rather than...
Targets with arrows.
Okay, thank you. I knew I should have brought my own laptop. So yes, this word that's marked n bits, that represents the phase of the signal that we're going to transmit. And every clock cycle, we add a constant amount to that. So we end up with the phase value just goes linearly up with time. Well, that's exactly what an analog oscillator does. We just have a digital implementation of it. And from that digital implementation, we add another word, delta phi, every clock cycle, so that our phase increases at the right rate for the frequency that we want. We then convert that to a sine wave signal using a lookup table to a sine value or a cosine value. The challenge to any of this is to make that happen in a digital implementation, and there usually has to be some kind of compromise because you can't implement that with all of the word sizes you would like to have. Ideally, where it says n bits, you'd like a 32-bit wide word. That would mean that you need memories that are 4,000 million locations long. Well, you can't get that in an FPGA. So the design that we had was the Xilinx 16-bit DDS. Well, if I made a perfect 16-bit DDS that had essentially that lookup table, had all 4,000 million locations, I'd get the signal that's on the left-hand side. And that's got some line spurious. Those are frequency dependent, and those are a consequence of using a 16-bit D2A converter at the end of this, but they're quite small in amplitude. And that's a pretty good signal. The 16-bit DDS that Xilinx can synthesize that fits in the the resources they can make available, it's got a signal like the middle graph. And the noise floor is a bit worse than minus 120 dBc. And that's the cause of the problem that we were having. Well, the next step I could easily go to was to make an 18-bit DDS. And that is the graph on the right. And as you can see, the noise floors come down by something like 10 dB, at least if you get away from the center. But two things are a problem here. First of all, you can see a shape that it's starting to trend to. That isn't actually the performance of the DDS at all. That's the performance of the FFT window that I was using to view the signal. So that's a measurement problem. But the other one, look at the figures in the top, that's now using 17 block memories. That's quite a lot to start using up in the FPGA. And we need to go further anyway, and we can't make all of the DDSs have more than 17 block RAMs. So I've got two problems here. One's a measurement one, and one is an implementation one. Well, let's tackle the measurement first. A fast Fourier transform is a way of estimating the spectrum of a digital signal. And we take n samples from that signal. So we take a block of n samples and process them. The problem is the FFT assumes that the next block of samples will just join on to the first ones that you had. And in almost all cases, you'll get a phase discontinuity. So we end up with the second down signal. We're trying to now estimate the spectrum of something that has a phase discontinuity in it, and that broadens the width of the signal that you see on the FFT output. We get round that by using what's called a window function. So we multiply the n samples by a signal whose shape in some way starts at 0 at the ends and goes to 1 in the middle. And that means that the energy at the edges of the FFT block is de-emphasized, and you can get an improvement in the estimate of the spectrum. So that's what FFT windowing is all about. The window I've drawn there really wouldn't be very good. But we can get to the point where the FFT then shows almost a single tone. Well, there are lots of window functions that are used in DSP. Probably as many as people who've done PhD degrees in signal processing. One that's commonly used, that I used to use, is the Blackman-Harris window at the top right. But that's the one that has got that shape that you saw in the picture earlier. But I then came across a window called the Blackman-Nuttall window, which has got much lower side lobes. And consequently, when I switched to that, the measurement problem has gone away. The other problem was to try and make an 18-bit DDS, I was using 17 block RAMs. If I'd wanted to make a 20-bit DDS, I was going to use probably 16 times that number. You just can't have that. So Xilinx have got a DDS compiler, which has a way of improving on that. It uses essentially an estimate of the phase of the signal by using a limited number of bits, and it truncates the width of that n-bit bus down to 11 bits, I think it is. But from the rest, that's an estimate of the error. So the error is then fed forward into a simple numerical algorithm, which does, as far as I know, a two-term approximation and brings about an improvement in the spurious signal level by essentially digitally correcting for that error. I found the paper that describes that algorithm, and the reference for that is there if you want to read about it. The net result is, if I go to a 21-bit DDS, I've used much less memory, but I'm starting to use some signal processing, essentially using 3 multipliers. But I've got quite a few multipliers available in the design, so that's not a problem. And the 21-bit DDS was pretty good. The 23-bit DDS is near enough perfect for our purposes. That used 3 block RAMs, which is less than I was originally using, but it does use 5 DSPs. The other way to get a sine and a cosine output is to use an algorithm called a CORDIC algorithm. Well, most DSP implementations that are used for SDR use a CORDIC, and the original HP SDR projects used a CORDIC. So I've taken the CORDIC algorithm from the HP SDR radios and essentially copied the Verilog and run that in my simulation. The CORDIC's an efficient algorithm to be able to rotate a vector, but without using multiplies that are anything other than multiplies by 2. The attraction of multiplying by 2 is that you can do that with bit shifts and adds rather than needing a proper multiplier. And it then uses an iterative algorithm that over several stages converges on the final result. That then means that you have several stages happening one after the other, so it starts to build up a little bit of latency, but 25 stages at 8 nanoseconds per stage isn't going to be noticeable to anybody. It's reasonably efficient. It uses something like 1,000 registers in total. Well, that's insignificant in modern FPGA, so you can have a CORDIC. So some simulation results with the CORDIC. The best the best DDS that I made in my FPGA using the Xilinx algorithm was the 23-bit Taylor series corrected one on the left. The CORDIC used by HPSDR projects is the 22-bit one in the middle, so it's got the same general shape but some line spurious that are visible. And I then modified that to be a 24-bit CORDIC, and the behavior of that is pretty much comparable with the Xilinx DDS. So I've got 2 options then to move forward. So putting it all back together, my starting point was the left-hand side. Working with the 23-bit Xilinx DDS, I get the figure on the right-hand side, so including all the rest of the chain, including the multiplies, the multiplies by the IQ signal and the output scaling, I get a little additional noise added, but basically much, much better than I was getting before. So, showing 2 plots of the original signal and the new signal side by side, there's pretty much a 25 dB difference between the 2. Well, that's more than 2 orders of magnitude. I really ought to have known better the first time. That's measured going all the way out to an RF signal and then being essentially measured by an A to D converter on the same board as the 2.5 watt exciter. There's got to be some coupling between that 2.5 watt exciter and the A to D converter. So it's not a perfect measurement, and if that was made on a separate receiver board, it would probably be a few dB better. But I've been able to make an improvement that gets us well into the minus 140 dBc per hertz at more than 10 kilohertz offset. In conclusion, the transmitter really was not as good as it should have been. And I've been able to explain why that's happened and be able to make an improvement. So I haven't stabbed in the dark. I can explain why it was bad before. I can explain why it's good now. This is an open source project, so all those users of G2 radios can download the new code and have that improvement straight away. There's a key lesson come out from this. It's just not good enough to essentially guess a number for the specification of the transmitter and then implement it. I need to be able to simulate that, and I really ought to have done better in the first place. But I have got a way of simulating it, and the results that I get measured at RF do behave at least in line with those simulations. The next improvement that I can make to the complete process is to try and make a complete simulation in Octave of both the transmit and receive process. so that I can predict the performance of both essentially before I've gone to the FPGA at all. And that's probably something I need to work on in the future. But I've been able to make an improvement. I've explained what that improvement was, and I've got a way of making measurements that seems to work. Any questions? Okay, so
Questions?
there's one near the back.
Yeah, okay, moment.
Hi. Actually, I have two questions, so it's fine. One, for DDS, the symmetry between the cosine and sine is taking into consideration to make the smallest table needed, I guess.
Well, that would show up in some of the simulations of the output. I will have been showing you the sine or the cosine, but the final signal that you've seen is the result of those going through a complex multiplier, so you see both. Essentially, you see both.
Okay. And the other question is, your Octave code is also on open source on
Yes, that's all in my GitHub repository.
Perfect.
It's not very good Octave code, but it's better than it was last year.
I have the exact same application as you, trying to analyze transmit noise, and I got the exact same problem, so I'm looking forward to trying your code. Thanks.
Okay.
Okay. Yeah, well, it's a big step to improve the phase noise of a transmitter. So it is a nice contribution to our conference. Thank you very much for that, Laurence.
Okay, there was one more question.
One more question, okay, moment.
When the full schematic of Saturn will be available?
Well, the schematic of the board isn't my product. You'd have to talk to Abby about that. Generally,
But
he
it's
does make...
nothing like, it's not source code or something else. People who work with that board should know what's there. They should send back to factory where there's problems with that to fix it, for example. I think it's a good point to show it to everywhere.
It's all the DSP is open source, and you can look at it. The PCB is not mine.
I'm not talking about PCB, only schematic. What you can see, parts on where it goes, not board. Board, I understand, that is a closet.
Okay.
Yeah. But
if you download my repository and open that in Vivado, you can see the schematic of the FPGA. Is that what you mean?
No. Fully understandable schematic, like all parts, like I don't know how to better say in English.
Perhaps we can talk about it outside.
Okay.
Yes.
Okay, thank you. So a big applause to Laurence.